Namaskar, I welcome all of you to my YouTube channel. This is lecture number 29 on complex analysis, and from today onwards I am going to start a very important topic, which is the calculus of residues. Now let me talk about what are the topics that I will be covering in my upcoming lectures. First, I will define what is residue at a pole. Next, different methods to find residue at poles. Here I will mention total 4 methods for finding residue at poles. The third topic will be Cauchy's residue theorem, and finally I will solve some numerical problems. Now let me define what is residue at a pole. Students, we know that according to Lorentz theorem we can expand a function f of z about a singular point z equal to a in this way. Here the coefficient of the term 1 by z minus a, that means b1, is known as the residue of the function f of z at z equal to a. গতিকে বুজি পোৱা গ'ল নে লৰেঞ্চ সিৰিজ এক্সপানশনৰ 1 by z minus a টাৰ্মটোৰ যিটো কোএফিচিয়েন্ট হয় মানে b1, ইয়াক কি বুলি কয় residue of the function f of z at z equal to a. Now let me read the definition. The term b1, that means this one, in Lorentz series expansion of f of z is called the residue of the function f of z at z equal to a. That is, residue at z equal to a is b1, which is the coefficient of the term 1 by z minus a. Okay? Now let us solve two numerical problems to understand the theory part. The problem says we have to find out the residue at z equal to 0 if number 1, f of z is equal to z into cos 1 by z, number 2, f of z is equal to sin z divided by z to the power 6. First, let me solve problem number 1. So according to problem number 1, f of z is equal to z into cos 1 by z. Now let us expand cos 1 by z term. So after expanding we will get z into 1 minus 1 by 2 factorial into 1 by z square plus 1 by 4 factorial into 1 by z to the power 4 minus dot dot dot. Next, let us multiply this term with this term. So finally we will get z minus 1 by 2 factorial into 1 by z plus 1 by 4 factorial into 1 by z cube minus dot dot dot. So therefore residue at z equal to 0 is equal to coefficient of the term 1 by z minus 0, that means 1 by z. Here we have seen that the coefficient of 1 by z is minus 1 by 2 factorial, and we know that 1 by 2 factorial is 1 by 2. So this is the answer. Next, let us solve problem number 2. So according to problem number 2, f of z is equal to sin z divided by z to the power 6. Again let us expand sin z term. So finally we will get z to the power 6 into z minus z cube divided by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial plus dot dot dot. Next, let us multiply this term with this term. So finally we will get 1 by z to the power 5 minus 1 by 3 factorial into 1 by z cube plus 1 by 5 factorial into 1 by z minus z divided by 7 factorial plus dot dot dot. So therefore residue at z equal to 0 is equal to coefficient of coefficient of 1 by z minus 0, that means 1 by z. Here we have seen that the coefficient of 1 by z is 1 by 5 factorial, which is equal to 1 by 120. So this is the answer. Okay. Next, let me teach you second topic. The second topic is different methods to find residue at poles. Students, here we will learn total 4 methods for finding residue at poles. However, in this lecture, I will teach you only 2 methods, method number 1 and method number 2 with examples. The remaining methods, method number 3 and method number 4, will be discussed in detail with examples in my next lecture. Now, let us learn method number 1. According to method number 1, if z equal to a is a simple pole or pole of order 1, then residue at z equal to a is given by limit z tends to a, z minus a into f of z. Next, method number 2. According to this method, if z equal to a is a simple pole and f of z is in this form phi z divided by psi z, where the value of psi at z equal to a is 0, but the value of phi at z equal to a is not equal to 0, then residue at z equal to a is given by limit z tends to a phi z divided by psi prime z, where psi prime z is equal to d dz of psi z. One very important point is that please apply method number 1 when the denominator is in factorized form, and please apply method number 2 when the denominator is in trigonometric form or is in algebraic form. Now, let us solve some numerical problems to understand method number 1 and method number 2 properly. The problem says we have to determine the poles and residue at the poles of the following functions. Number 1, f of z is equal to z divided by z minus 1. Number 2, f of z is equal to 1 minus twice z divided by z into z minus 1 into z minus 2. Now, let us solve problem number 1. So, given f of z is equal to z divided by z minus 1. We know that singular points or poles can be obtained by putting the denominator equal to 0. So, if we do, then we have seen that z equal to 1 is a simple pole or pole of order 1. Let me write these points. Poles of the function f of z can be obtained by putting the denominator equal to 0, that is z minus 1 is equal to 0. This implies z equal to 1, which is a simple pole. So, we will apply method number 1 for finding residue at z equal to 1. Therefore, residue at z equal to 1 is given by limit z tends to 1 z minus 1 into f of z. According to our problem, f of z is equal to z divided by z minus 1. Now, let us substitute f of z here. So, finally, we will get limit z tends to 1 z minus 1 into z divided by z minus 1. So, z minus 1 will be cancelled out. So, finally, we will get limit z tends to 1 z. So, if we substitute the limit, we will get the residue at z equal to 1 is equal to 1. This is the answer. Next, let me solve problem number 2. According to problem number 2, f of z is equal to 1 minus twice z divided by z into z minus 1 into z minus 2. Here, we have seen that z equal to 0, 1 and 2 are the simple poles. First, let me write these points. the poles of the function f of z can be obtained by putting the denominator equal to 0, that is z into z minus 1 into z minus 2 equal to 0. This implies z equal to 0, 1 and 2. These are the simple poles. These are the simple poles. So therefore, residue at z equal to 0 is given by limit z tends to 0, z minus 0 into f of z. So this implies limit z tends to 0, z minus 0 means z, and according to this problem f of z equal to 1 minus twice z divided by z into z minus 1 into z minus 2. So this z and this z will be cancelled out. So finally we will get limit z tends to 0, 1 minus twice z divided by z minus 1 into z minus 2. If we substitute the limit here, then we will get 1 minus 0 divided by 0 minus 1 into 0 minus 2. So finally we will get 1 by 2. So therefore the residue at z equal to 0 is 1 by 2. Next, let us find out residue at z equal to 1. Again, residue at z equal to 1 is equal to limit z tends to 1, z minus 1 into f of z, which is 1 minus twice z divided by z into z minus 1 into z minus 2. So this term and this term will be cancelled out. So finally we will get limit z tends to 1, 1 minus twice z divided by z into z minus 2. If we substitute the limit here, then we will get the residue at z equal to 1 equal to 1. Finally, let us find out the value of residue at z equal to 2. So therefore, residue at z equal to 2 is given by limit z tends to 2, z minus 2 into f of z, which is equal to 1 minus twice z divided by z into z minus 1 into z minus 2. Now let us cancel out this term and this term. So finally we will get limit z tends to 2, 1 minus twice z divided by z into z minus 1. Now let us substitute the limits. If we substitute the limit, then we will get residue at z equal to 2 is minus 3 by 2. So this is the answer. Finally, let me solve two numerical problems to understand the method number 2. According to this problem, determine the poles and residue at each pole of the following functions. Number 1, f of z is equal to cot z. Number 2, f of z is equal to z divided by sin z. Now let me solve problem number 1. So given f of z is equal to cot z. This cot z can be written as cos z divided by sin z. Here we have seen that the function f of z is in this form, phi z divided by psi z, where phi z is equal to cos z and psi z is equal to sin z. Now let us find out the poles. We know the poles of the function f of z can be obtained by putting the denominator equal to 0. That is sin z is equal to 0. So therefore z will be equal to n pi, where n is equal to 0, plus minus 1, plus minus 2, comma plus minus 3 dot dot dot. Here we have seen that the value of psi at z equal to n pi is equal to 0, and value of phi at z equal to n pi is not equal to 0. So therefore we will use method number 2 for finding the value of residue at z equal to n pi. So therefore residue at z equal to n pi is equal to limit z tends to n pi phi z means cos z, divided by psi prime z, that means ddz of sin z. So after simplifying we will get limit z tends to n pi cos z divided by dz of sin z is equal to cos z. If we substitute z equal to n pi here, so finally we will get the value of residue at z equal to n pi is equal to 1, which is the answer. Next, let me solve problem number 2. According to problem number 2, f of z is equal to z divided by sin z. Here also we have seen that f of z is in this form, where the value of phi z is equal to z and the value of psi z is equal to sin z. Again, the poles of the function f of z can be obtained by putting the denominator equal to 0. That means sin z is equal to 0. Here we obtain z equal to n pi, where n equal to 0, plus minus 1, plus minus 2, plus minus 3 dot dot dot. Again we have seen that the value of psi at z equal to n pi is 0 and the value of phi at z equal to n pi not equal to 0. So definitely we will use method number 2 for finding the value of residue at z equal to n pi. So therefore residue at z equal to n pi will be limit z tends to n pi z divided by dz of sin z. After simplifying we will get limit z tends to n pi z divided by dz of sin z is equal to cos z. Now let us substitute the limit. So finally we will get n pi divided by cos n pi, which is equal to n pi divided by cos n pi value is minus 1 whole to the power n. So the value of residue at z equal to n pi is n pi divided by minus 1 whole to the power n. This is the answer. This is all about today's video, and I hope that you have learnt a lot from this video.